Hello students, welcome to the Optics lecture series by Pandit Deendayal Petroleum University. This is Dr. Sheetal Rawat. This is the fourth lecture today. Up till now, we have covered the sinusoidal waves, introduced interference and the principle of superposition, constructive and destructive interference conditions, interference by two methods. One is division of wavefront, second division of amplitude. For that we have done double slit and the Newton's ring experiment. Now coming to the application part of the interference. Where here the anti-reflecting films, they utilize the phenomena of interference, that is a destructive interference, and they are used in number of lenses. A thin coating of the anti-reflecting film is coated on the lens surface or the glass surface, which prevents us from the glare and the reflectance losses. Every one of you must have seen this colorful pattern in the soap bubbles. This pattern is observed due to the thin film interference between the soap bubbles. Again, it uses the concept of division by amplitude method, and these colorful patterns are because of the presence of or the interference due to the white light instead of the monochromatic light. One of the important applications of thin film interference is in the reduction of the reflectivity of the lens surface. Anti-reflecting film is a type of optical coating that is applied to the surface of lenses and other optical elements to reduce reflection. For better understanding, we can assume that when a light beam going from medium 1 having refractive index N1 is incident normally on a dielectric of refractive index N2, then the amplitude of the reflected and the transmitted beams are related to that of the incident beam through the following relation, where AR is my amplitude of the reflected beam, AI is the amplitude of the incident beam. AT is the amplitude of the transmitted beam. In the first equation or in the second equation is what is the amplitude of the transmitted beam with respect to the amplitude of the incident beam. When N2, that is the refractive index of the second medium, is greater than the refractive index of the first medium, then my AR, amplitude of the reflected beam, is negative, as seen from the equation 1, showing that when reflection occurs at denser medium, that is from rarer to denser medium, a phase change of pi occurs. This we discussed in the last lecture also. The amplitude of reflection and transmission coefficient R and T, they are given by the following relation. R equals to N1 minus N2 divided by N1 plus N2. T is given by twice N1 by N1 minus N2. You need to remember these terms. That is the coefficient of reflection and transmission. If R dash and T dash are the reflection and the transmission coefficients, when the light propagating in the medium of refractive index N2 is incident on a medium of refractive index N1, then my R dash becomes N2 minus N1 by N1 plus N2, or equals to minus of R, just by interchanging N1 and N2, because now my incident beam is going from medium N2 to medium N1. We will just interchange N1 and N2. Rest equations will be same. T dash becomes similarly twice of N2 by N1 minus N2. R dash equals to minus R represents that when a light beam passes from rarer medium to denser medium, then on reflectance or on reflection, a phase change of pi occur. This is the diagrammatic representation of whatever we have talked, that is from rarer to denser medium in figure A and from denser to rarer medium in figure B. Equations 4 and 5, they represent Stokes' relation. 1 minus T dash equals to R square. This relation gives us the value of the reflection coefficient. In many optical instruments, there are many interfaces and loss of intensity due to reflection can be very effective. This phenomena is extracted by the anti-reflecting films to suppress the relation and, and reduce the glare. This relation we also obtain while doing optical reversibility, if you remember in lecture 2, and 3. For example, for normal incidence, reflection of ground glass surface in air is given by n minus 1 by n plus 1 whole square, which is around 0.04. This means that 4% of the light is reflected when the light is normally incident on a ground glass. Reflectance equals to 0.04 means that 4% of the incident light is reflected. For n equals to 1.67, using the formula we get that 6% of the light is reflected. Thus, if we have large number of surfaces, the losses at the interface will be very considerable. In order to of these losses, lenses are often coated with lambda by 4n thick non-reflecting films. Non-reflecting films are the films which minimize the losses and prevent the glass from the glare. The refractive index of the film being less than that for the lens. For example, a glass of refractive index 1.5, if coated with MgF2 film, then the film's thickness D should be such that the part difference equals to the condition of destructive interference, that is half lambda, and it is equals to D equals to lambda by 4NF. D equals to lambda by 4NF expression gives us the optimized thickness of the anti-reflecting film, which should be coated in the surface of the glass usually, so that we get minimum reflectance and the glare is minimum and most of the light gets transmitted, so that minimum losses occur. Here, if we assume that for the normal incidence and NF of the MgF2 film is 1.38, this is the anti-reflecting film. Thus, for lambda equals to 5.0 10 to the power minus 5 centimeter, we'll have the thickness of MgF2 film equals to 0.9 to the power minus 5 centimeter, which will make sure that the reflected lights interfere destructively and minimum reflectance occurs, which is in case of glasses. Therefore, in order to get rid of the unwanted interference on camera lenses, which are usually made up of glass, they use appropriate anti-reflecting film coatings. Here, coatings, they get rid of the reflecting light of the middle spectrum, so that therefore, because of this anti-reflecting coating, our lenses or the camera lenses, as you can see here, it appears red or violet. Representation of how a coating of non-reflecting film or anti-reflecting film helps to reduce the reflection. If a light, it goes from the air having refractive index 1 and falls on the non-reflecting film of the thickness, that is lambda by 4NF, and the refractive index of the film is less than the refractive index of the glass surface on which it is coated, then the reflected light from the first or the upper surface of the non-reflecting film and from the interface surface of non-reflecting film and the glass, that is the 5, 2 and 5, they are made to interfere destructively, and this makes the reflectance very less compared to the no compared to no coating of the non-reflecting film on the glass surface. Now, how to choose the anti-reflecting film that is to be coated on the surface? That is, what should be the refractive index of the non-reflecting film? For that, let's just do some mathematics, some calculations here. Let NA, NF and NG be the refractive index of air, non-reflecting film and the glass respectively. See in the figure, adjacent figure. If A is the amplitude of the reflected wave, then the amplitude of reflected and refracted would be, as from the expressions as discussed before, will be, that is, for the reflected will be minus of NF minus NA by NF plus NA incident amplitude, or the refracted or transmitted will be 2 NA by NF plus NA K. A is the incident amplitude respectively. The amplitude of the waves corresponding to rays 4 and 5 are to be calculated so that we put a condition and find out what should be the refractive index of the non-reflecting film. Now 2 and 3 we know. Thickness we know, which is lambda by 4 NF of the non-reflecting film. In order to find out 4 and 5, only change will be, instead of the amplitude A, we will now be using the amplitude of 3 for the 4 wave, which is getting reflected. 3 wave is getting reflected. We just replace the amplitude A with the amplitude of the wave 3, whereas the 5 is the transmitted wave of the fourth, which of the 4. That is, for finding out 5, we will just be replacing the amplitude of 4 in the transmitted equation. For complete destructive interference, the rays corresponding to rays 2 and 5 should have same amplitude. Therefore, they will cancel out each other and form a dark, that is, no fringe. Should have same amplitude, that is, we will equate the amplitude of 2. After simplifying the equations, we get equation 9, where we have used the fact that 4 Na by Nf divided by Nf by Na by whole square, this is equals to 1. This we can prove also. What we take some values, say for example Na is 1, that is refractive index of air is 1, Nf say for around 1.4, then this expression, that is 10 equation, will be around 0.97 equal, which is approximately equals to 1. That is, our assumption is okay. Hence, on simplification, we get NF, that is refractive index of the film, anti-refracting film, which is to be coated on the surface of the glass. It should be around the square root of the refractive index of the glass and the refractive index of the air. Since the refractive index of the air is taken as 1, then my expression reduces to that the square root of the refractive index of the glass should be the refractive index of the film that is to be coated on its surface for better results. For Na equals to 1 and Ng equals to 1.66, and using the relation just obtained earlier, that is Nf equals to under root of Na Ng, my Nf comes out to be 1.29. The optimized thickness for the anti-reflecting film is around lambda by 4n. Then my reflectivity will become this, that given in equation 12. If we again change the Ng to 1.5, then my NF becomes 1.33, and I measure the reflectivity or calculate the reflectivity, it comes out to be 1.3%. However, in the absence of the film, it would have been 4%. Now you can see here the reflectivity has decreased from 4% to mere 1.3%. This has resulted in the less glare, minimum losses, and most of the light is getting transmitted. Now, this technique of reducing reflectivity is called as blooming. After anti-reflecting film, we have Michelson interferometer, which uses the phenomena of interference. Michelson interferometer was invented by the American physicist Albert A. Michelson in 1852. It is a precision instrument that produces interference fringes by splitting a light beam into two parts and then recombining them after they have traveled different optical paths. In the figure, this it depicts that the interferometer and the path of a light beam from the extended source S, which is usually a ground glass plate that diffuses the light from the monochromatic lamp. The beam strikes the half-silvered mirror G1, where half of it is reflected to the side and half passes through the mirror G1. The reflected light, it travels to the movable plane mirror M1, where it is reflected back through G1. The transmitted half of the original beam is reflected back by the stationary mirror M2 and then towards the observer by the G1. The terms used in the figure: S is the source of light, L is the glass plate so that an extended source of almost uniform intensity is formed, G1 is the beam splitter. The incident beam is partially reflected and partially transmitted to the respective mirrors M1 and M2. One is the movable, another one is the fixed. Usually M2 is the fixed and M1 is the movable. In normal adjustment of the interferometer, M1 and M2, they are perpendicular to each other and G1 is usually kept at an angle of 45 degrees with the mirror. The Michelson interferometer and how it produces interference patterns. This is the schematic diagram how the interference pattern or the light reflection transmission takes place inside the interferometer. Beam from a extended source S falls on the beam splitter, which partially reflects and transmits the light. 1 and 2 are the reflected in the transmitted light. They fall on M1 and M2, two mirrors. One is the movable, another is a fixed one. The beam or the light further gets reflected from the mirrors and falls back on the beam splitter, where they again gets reflected and a path difference gets introduced between them. The reflected lights from the beam splitter are 5 and 6, which subsequently meet somewhere and interfere and form interference pattern. Here is the working in following steps. You can go through it one by one. I have explained this to you earlier. One thing I would like to point out is that the 5 and 6, the reflected beam from all the process from beam splitter, it appears to our eyes that they are emanating or emerging from P, and they are getting reflected by two parallel mirrors M1 and M2 dash separated by a distance x1 minus x2. One more thing, if we use an extended source, then no definite interference pattern will be obtained on the photographic plate placed at the position of the eye. Instead, if we have a camera focus for infinity, then the focal plane will obtain circular fringe pattern and each circle corresponds to a definite value of theta. The beam splitter G1 is a glass plate. Therefore, the beam reflected from M2, that is the fixed mirror, will undergo a phase change of pi, as discussed before, that on reflection, a phase change of pi occurs when a light goes from rarer to denser medium. And since the extra path that one of the beam will traverse, that will be around twice of x1 minus x2, that is, it will go and come back, therefore twice. The condition for destructive interference would be 2d path difference equals to m lambda. Why m lambda? Because here the interference is taking place due to the division of amplitude, where my small d equals to x1 minus x2. And angle theta, it represents the angle that the rays make with the axis which is normal to the mirror. This is same as what we did when the interference through a film takes place. Similarly, the condition for constructive interference will be 2d path difference equals to m plus half lambda. After the constructive and destructive interference conditions, in order to calculate the angle at which the dark ring will appear, we will be using the destructive condition, interference condition. For example, let's take lambda is 6 into 10 to the minus 5 centimeters and d equals to 0.3 mm. We'll be getting dark ring at angle 0 degree, 2.56 degree, corresponding to m equals to 1999 and so on. Therefore, we'll be getting a central dark ring corresponds to m 1000 and 999 as shown in the figure. This is the kind of pattern that you get from the Michelson interferometer. These are the concentric, dark and the bright fringes corresponding to d equals to 0.3 mm and m equals to 1000, 999, 998 and so on. Shows two interference patterns corresponding to d equals to 0.15 mm and d equals to 0.14985 mm. For d equals 0.15 mm, we have seen what is my theta corresponding to that m. For d equals to 0.14985 mm, my theta will be 0 degree, 3.62 degree and so on, corresponding to m equals to 500, 499 and so on. This states that if we start reducing the value of d, here we have decreased from the d equals 0.15 to 0.14985 mm, the fringes, they appear to collapse at the center and the fringes become less closely spaced. It can be clearly seen from the two figures. Now, if d is further decreased, say 0.15 to this, then it becomes 2d equals to 499.5 lambda. From the two figures, we can see that the dark central spot in the left hand side figure has been disappeared in the right hand side figure and a central fringe has appeared, which is bright. Thus, if d is decreased, the fringe pattern, they tend to collapse towards the center, or if the d is increased, the fringe pattern, they expand. Hence, if n number of fringes collapse to the center as the mirror m1 moves through a distance d0, then we must have 2d equals to m lambda. And for the d0 thing we have, and the equations become 2d minus d0 equals to m plus capital N lambda, or simply the wavelength of light can be measured as 2d0 by capital N. Thus, by moving the mirror through a distance, we can observe that a number of n fringes, they have moved through a point on the screen, which is useful in calculating the wavelength. Now, for example, for a typical experiment, if one finds out 1000 fringes, that is n equals to 1000, they collapse to the center as the mirror is moved through a distance of 2.90 to the power minus 2. Then from the expression we find out the wavelength of the light source will be lambda equals to 5800 angstrom. Therefore, we use Michelson's interferometer to find out the wavelength, thickness of the film, and so on. The above mentioned was also used by the Michelson for the standardization of the mirror. With this, we have covered everything in the interference, that is superposition principle, destructive and constructive interference, division by wavefront, double slit, division by amplitude, Newton's ring, anti-reflecting film, what are their uses, how they work, what is their thickness, Michelson interferometer, and everything. Thank you.